say you put down a point charge Q. It's going to create an electric field at every point in space around it. If the charge is positive, the electric field is going to point radially outward from the charge. The units of electric field are newtons per coulomb because it tells you how many newtons of force there would be on a 1 coulomb charge placed at that point. You can use the formula kq over r squared to find the size of the electric field. Q refers to the charge that's creating the electric field. R refers to the distance between the charge creating the field and the point in space where you're determining the electric field. Since the electric field's a vector, you have to worry about breaking it into components. If some other charge creates its own electric field contribution at that point in space, in order to find the total electric field, you have to break up both electric fields into components. You'd add up the x components, then add up the y components, and use the Pythagorean theorem to find the size of the total electric field at that point in space. This charge Q that we've drawn not only creates an electric field at every point in space around it, it also creates an electric potential V at every point in space around it. The electric potential is not a vector, it's just a number that's either positive or negative, and it's measured in joules per coulomb because it tells you how many joules of potential energy a 1 coulomb charge would have if placed at that point in space. You could use the formula kq over r to determine the electric potential created by a point charge. Q is the charge creating the electric potential, and r is the distance from the charge to the point in space where you're determining the electric potential. Using this formula is much easier than using the electric field formula because the electric potential is not a vector. That means it has no direction and no components. You literally just plug in the plus and minus signs for the charge and add up the contributions from all the charges. A positive charge will always create a positive electric potential, and a negative charge will always create a negative electric potential. A negative electric potential does not mean it points down or left, it just means that the number for the electric potential is a negative number. If you place an additional charge into this diagram, you'll get an electric force equal to kqq over r squared. This time r refers to the distance between the two charges that are interacting. Note that even if one charge is very big and one charge is very small, they will still exert equal and opposite forces on each other because of Newton's third law. You shouldn't always use this formula kqq over r squared to determine the electric force though. If you know the electric field, more likely you're going to use the formula F equals QE. Q times E is a much easier way to find the electric force, and sometimes the only way you can find the electric force on a charge. Remember that the force on a positive charge points in the direction of the electric field, and the force on a negative charge points in the opposite direction of the electric field. So if you already know the electric field, for God's sakes, just use F equals Q times E. In fact, you can't even use F equals kqq over r squared if you don't know the location of every single point charge. Remember that electric force is a vector, so if it points in a weird direction, you have to break it up into components just like you do for the electric field. You can find the electric potential energy that exists between 2 point charges using the formula kqq over r. R again is the distance between the two charges, and just like F equals QE is a much easier way to find the electric force than kqq over r squared, PE equals Q times V is a much easier way to find the electric potential energy than kqq over r. So if you already know the electric potential at a point in space, just multiply Q times V to find the electric potential energy. And again, since you're dealing with electric potential, you do plug in the positive and negative signs for the charge. The formula that relates the electric field to the electric potential is E equals negative delta V over delta X. In other words, if you take the electric potential difference between 2 points in space, the voltage, and you divide that by the distance between those 2 points in space, you'll get the size of the electric field. The negative sign's just telling you that the electric field always points toward lower electric potential. If you have a charge of positive 3q, a distance d above a charge of negative 5q, and you want to determine the total electric field at a distance c to the right of them, you first draw the contributions to the electric field that each makes at that point. Then use kq over r squared to find the electric field that each charge makes at that point. For the positive 3q, you're going to have to determine the distance from the positive 3q to that point in space by using the Pythagorean theorem. Find the contribution by the negative 5q also by using kq over r squared. Now break up any diagonal vectors into x and y components. You may have to find the angle involved in the problem by using some trigonometry like inverse tangent. The horizontal piece here is going to be e sine theta, and the vertical piece is going to be e cosine theta. Now take that x component and subtract the contribution from the negative 5q charge since that points leftward. This gives you the x component of the total electric field. Since there is only one y component, this is going to be the y component for the total electric field. Now you can use the Pythagorean theorem to find the magnitude of the total electric field vector at that point in space. If you wanted to find the total electric potential at the other corner of the rectangle, it would be much easier since the electric potential is not a vector and it has no components. Just use kq over r to find the contribution that each charge makes at that point in space, including negative signs if there are any negative charges, and you literally just add up each contribution. No directions, no vectors, no angles, no components. Electric field lines point radially outward from a positive charge and they point radially inward towards a negative charge. A positive and negative charge placed next to each other is called an electric dipole. One of the rules for electric field diagrams is that the electric field will be largest where the electric field lines are most closely packed together. If you were to put two positive charges or two negative charges next to each other, they would create an electric field diagram that looks something like this. Another rule for the electric field line diagrams is that the electric field lines can never ever cross. Equipotential lines are lines through space where the V value, the electric potential, is constant along that line. Equipotential lines must always be perpendicular to the electric field lines in a region. Also, where the equipotential lines are most closely packed together, that's where the electric field is going to be greatest. And again, remember, the electric field lines always have to point toward lower V, or lower electric potential. For a parallel plate capacitor, the plates are equipotential lines since the V is constant on each plate. The electric potential will drop uniformly from the positive plate to the negative plate, so we draw the equipotential lines vertically in this example. And as always, the electric field points toward lower electric potential.